Section 1.3, solving equations with variables on both sides. Very similar to the last topic we covered, which is multi-step equations. We're just going to take it one step further, where now the variables appear on both sides of the equation. First of all, if it's possible, we want to simplify both sides of the equation. So the example that we have here, I can simplify actually both sides of the equation using the distributive property, distributing the 2 on the left side and the 0.5 on the other side. And so when I do that, I get 2 times 3x is 6x, and 2 times negative 4 is negative 8, equals 0.5 times 10 and 0.5 times negative x. Well, 0.5 is the same as 1/2, so half of 10 is 5. And then I'm actually going to choose to write it as a fraction, minus 1/2 x, instead of writing it as 0.5x. Now what I want to do is I want to look at step 2 here, which is to use inverse operations to bring all variable terms together, combining like terms. So here I have a variable term on the right, here I have a variable term on the left. I want to get them together by using inverse operations. I'm going to move that negative 1/2 x to the left by adding 1/2 x to each side. Notice that I'm adding it to both sides of the equation. The equal sign is still basically a fence. I have to do the same thing on each side of the fence. So this is going to give me, when I combine like terms, 6 and 1/2 x minus 8 equals 5. And now I have an equation that I can solve. I'm going to use inverse operations, go backwards through the order of operations, so I have to add 8 to each side, which brings me to 6 and 1/2 x equals 13. And that's actually tough to divide by a mixed number, so I'm going to turn that into a improper fraction by doing 2 times 6 is 12, plus 1 is 13, so I have 13 over 2x equals 13. And now, in order to cancel this out, get rid of that 13 over 2, I have to divide by 13 over 2, which I know is the same thing as multiplying by the reciprocal. So I'm going to multiply by 12 over 13. I'm going to do that on both sides. I'm sorry, 2 over 13. And maybe it helps make that 13 over 1. This will, everything will cancel out kind of nicely over here, leaving me with just x. And then I get something actually that cancels out here. I actually cancel out the 13s, and I'm left with 2 over 1. If I had done 26 over 13, it would have reduced, and I would have gotten x equals 2. And that's my solution. That's just using the step 3 here. I'm solving that equation using inverse operations. And finally, it's important to go in and check our work. So let's give ourselves some space to do that. And I'm just going to take that 2 and plug it back into my original equation that I had up here. And hopefully I get the same thing on both sides of the equation. So that's going to be 2 times 3 times 2 minus 4 equals 0.5 times 10 minus 2. And I'm going to check if that's true. I'm just going to go through and simplify that each side. And you can see that when I'm doing my check there, I end up getting 4 equals 4, which is a true statement. So that check indicates that I have solved this equation correctly, and x equals 2 is my solution. All right, now it's your turn. So what I'd like you to do is pause the video, try to solve each of these problems, and then come back and see how you did. All right, how did it go? All right, so there we go. The equation on the left is pretty straightforward. Nothing to simplify, so we just use inverse operations to move the 3p over to combine with the 5p, and we get p equals 3. Leave the check for you. And on the right equation, a little bit more complicated. Just a little distributive property with our fraction. Moved the 5h to the left by adding it to each side. Then isolated the h, and I get 3 divided by 8, which I'm just going to express as 3/8. A lot of people think that when they get a fraction, they did it wrong. But fractions are oftentimes our answers. So you can leave it just as 3/8, as long as you make sure the fraction's reduced, you're fine. And in this case, it is. It's a reduced fraction. You could make it 0.375 by doing the division, but there's no reason to do that. You're completely fine with h equals 3/8. All right, hope this was clear. Let's see a couple more examples. All right, so here we're going to talk about a couple of special cases. It's going to be kind of interesting here. I want you to go ahead and try to solve each equation, and you may find that you get to kind of a weird place in each one. So pause the video, try to solve each one, and then come back. We're going to see what strange thing just happened. Okay, so this looks a little bit different. On the left side, when we solve, we end up getting 21 equals 21. Seems obvious. Seems like it works. Okay, that's. But what happened to the variable? Well, the variables disappeared in this step here. Both sides had a negative 7w, and so what was left was just the expression 21 equals 21. Now, if this was a check, that would be great. I mean, the answer we had plugged in worked, but we didn't plug anything in here. So what this means is that we actually have a special case where everything's going to work. We have an infinite number of solutions. More specifically, we have all real numbers are solutions. Any number, positive, negative, decimal, fraction, doesn't matter. Anything you plug in will make the equation true because the equation just reduces down to the true statement 21 equals 21. So that's a special case. When you get the variables to cancel out and you have a true statement, you get infinite solutions, specifically all real numbers. In the second example, we end up getting negative 4 equals 0, which absolutely is not true. That is wrong. That's false. When that happens, it means that whatever we plugged in would be wrong, so the check wouldn't have worked. But again, we didn't plug anything in because the variable had just disappeared in the previous step when we subtracted 12d from each side. So when we get a false statement, instead of having infinite solutions, which is the special case of all, we have a special case of nothing, or what we call no solution. And so when you go ahead and solve the equation and you end up getting a variable to cancel out completely, and you're left with a false statement, you have no solution. Anything you plug in for D will fail to make the equation true. All right, I hope that is clear. All right, to wrap up today's lesson, let's talk about a word problem. Mr. Calnan has two different options when he registers students for the math team. He can either pay a $24 registration fee and then pay $7 per student, or he can skip the registration fee, paying $9 per student. Which is the better deal if he brings 4 students? What about 20 students? And is there a number of mathletes that would make the two options equal? All right, so let's figure out how we could express each of these options. We have the first option with the registration fee, and we could model it with this expression. We could call that 24 plus 7x, where the $24 is the flat fee to start, and then it's $7 times the number of students, and x would be the number of students there. Then we have the second option, which could be shown by this expression. There is no registration fee in this case, so it's just $9 per student, so 9 times x, where x is again the number of students. All right, so what if we only had 4 students? Well, in that case, we could figure out the total cost with each option by plugging 4 in for x. So go ahead and give that a shot, and you can pause the video and come back and see the answer. All right, let's see it. So by plugging in, we see that the second option here would only cost $36, as opposed to the first option, which would cost $52. So clearly this is preferable. What about 20 students? Is there make a difference then? All right, once again, pause the video, try to figure out the cost, then come back and double check. All right, so if we bring 20 students, the first option now only costs $164, whereas the second one costs $180, so the first option is better. So the question is there a number of mathletes that would make the two options equal? Well, in order to find out, I'm just going to take the two options and set up an equation. I'm going to have 9x equaling 24 plus 7x. And now I go ahead and I solve this equation here. I'm going to start by subtracting 7x from each side, which brings me to 2x equals 24, and then dividing by 2, I get my answer of x equals 12. If I bring 12 students, it should be equal. A quick check by multiplying 9 by 12 would reveal that would cost $108 using the second option, and using the first option would be 7 times 12, which is $84, plus the $24 registration fee also gives us $108. So with 12 students, the two options would be identical. So this is just an example of how you can set up and then solve a word problem using an equation that has variables on both sides. All right, I hope that this was helpful and that now you feel more confident on this material.